Here's an example. In Module 17, we talked about the table 5.7 of the textbook, and that electrical discharge machining example. Machining example where what was under discussion was angles of drilled holes, and in that table there was a sample of size 50 that had a standard deviation, had a mean of 44.117 degrees and a standard deviation of 0.984 degrees. And the idea here is I want to think about saying, well, what does this sample tell me about, say, a 51st, not 1 through 50, but one more angle drilled by this process. And what I need to do is to take the mean, which is 44.117, and hedge it to the right and to the left a t-value times 0.984, that's the standard deviation, times the square root of 1 plus 1 over 50. So 1 plus 1 over 50, and what goes here is, say, for 95% limits, what I need is the upper 2.5% point of the t-distribution with sample size minus 1, 49 degrees of freedom, and using jump or some other statistical package or interpolating in a table, that number is about 2.01. When all is said and done here, this is 1.998, and we end up saying, well, if I'm trying to tell you where one more angle from this process is likely to fall, I will have to take the sample average for the data in hand and hedge it by about plus or minus 2 degrees. Okay, so that in some sense I'm quote unquote 95% sure that this set of limits will capture one more angle from this process. This 95%, how do I interpret that? Well, that 95% is a lifetime batting average in some sense. For the process that takes a sample, computes limits, looks at one more observation, and sees whether or not the interval works. And I either win or lose on that series of steps, and the 95% says that 95% of the time that I would go through that whole series of steps, I would have an interval that in fact works in the sense that it captures the new outcome. new observation.